In this module, we introduce fluorescence spectroscopy. Fluorescence is a photophysical process in which certain molecules, after absorbing light, emit light of a longer wavelength than the absorbed light. This emitted light is observed as fluorescence. Fluorescence is distinct from phosphorescence, another type of luminescence, in its duration and mechanism. While fluorescence occurs almost instantaneously and ceases as soon as the exciting radiation is removed, phosphorescence can persist for longer durations, ranging from fractions of seconds to hours. This difference suggests that fluorescence involves a rapid conversion of absorbed radiation into re-emitted energy, whereas phosphorescence involves a slower release of stored energy. The figure on the left presents a Jablonski diagram, which is a graphical representation used to illustrate various photophysical processes within a molecule. The straight lines in the diagram represents radiative processes, while the wavy lines indicate non-radiative transitions. At the base, we have the ground electronic state denoted as S0. This is the state where the molecule typically resides. The first excited singlet and triplet states are denoted as S1 and T1. When a molecule absorbs light, it gets excited both electronically and vibrationally, transitioning to a higher energy electronic state S1. As the molecule interacts with its surroundings, especially in a solution or gas, it undergoes collisions with other molecules. Through these collisions, it loses some of its energy non-radiatively, descending to lower vibrational levels of the excited electronic state. This process is known as vibrational relaxation. From these lowest vibrational levels, the molecule can emit light and return to the electronic ground state. This radiative process where light is emitted is what we observe as fluorescence. To summarize, fluorescence is a multi-step process starting with absorption, followed by vibrational relaxation and culminating in the emission of light. Fluorescence spectroscopy is a prime example of emission spectroscopy. Generally, to obtain a fluorescence spectrum of a sample, we first have to illuminate it with light. This light is typically of a specific wavelength. When the sample absorbs this light, its molecules get excited and move to a higher energy electronic state. This is what we refer to as the excitation step. These excited molecules soon return to their ground electronic state. And as they do, they emit light. This emitted light is what we call fluorescence. From the point of view of instrumentation, the illumination of the sample is done essentially in the same way as discussed for UV with absorption spectroscopy. The specificity of fluorescence spectroscopy is related in the detection of the fluorescent light emitted by the sample molecules. In absorption spectroscopy, we measure how much of the original light intensity at a specific wavelength had left after passing through the sample. In fluorescence spectroscopy, after the sample has been illuminated, some of its molecules fluoresce, emitting light in all directions. Some of this fluorescent light passes through a second filter or monochromator and reaches a detector. These detectors, such as photomultiplier tubes or photodiodes, are capable of converting weak fluorescence into an electric signal. This allows us to measure the intensity of the fluorescent light at different wavelengths. During the measurements, we do not want the original excitation light to interfere with the emitted light. To minimize the risk of transmitted or reflected incident light reaching the detector, it is typically placed at a 90 degrees angle to the incident light beam. Fluorescence spectroscopy offers a unique perspective on molecular behavior, especially when we examine the fluorescence spectrum. As depicted in this figure, we can observe the relationship between absorption and fluorescence bands. Let's start with a fundamental observation. The fluorescence emitted by a molecule typically has a lower frequency than the light it originally absorbed. This is due to the vibrational relaxation that occurs before fluorescence. After a molecule absorbs light and gets excited, it loses some of its energy through non-radiative processes, like collisions with surrounding molecules. This energy loss causes the emitted fluorescence to be of a lower energy than the absorbed light. Now, looking at our figure, the absorption spectrum on the right showcases vibrational structures characteristic of the upper electronic state. In contrast, the fluorescence spectrum on the left reflects the vibrational structures of the lower electronic state. This difference arises because the fluorescence emission happens after the molecule has undergone vibrational relaxation, settling into the lowest vibrational level of its excited state. An intriguing aspect of this spectra is their symmetry. If you observe closely, the absorption and fluorescence spectra often appear as mirror images of each other. The practical implications of these observations are substantial. For instance, the vibrant colors we see in fluorescent dyes, like bright oranges and greens, arise from this mechanism. These dyes absorb ultraviolet and blue light but fluoresce in the visible spectrum. The fluorescence spectrum provides a wealth of information about molecular interactions, energy transitions, and the environment in which these molecules reside. The intensity of this fluorescence can also provide insights into the solvent's properties, as some solvents can quench the fluorescence, offering valuable kinetic information.